you everyone for joining our webinar. This is exciting because it is part 3 of our series, and we will have one more part that we will be having in November, and we will have some special guests on that as well. So just keep an eye out on our social media for that, but we're excited to get this one going as well. If you missed part 1 or part 2, don't worry. Alex will be going over a couple things that were talked about in those webinars, so you're not missing out. But you can always go to our YouTube page and watch the recording of those 2 webinars as well. If you haven't met me yet before, my name is Ruthie Senanayaka, and I work on the marketing team here at Blueprint. And if you are not too familiar with Blueprint, I want to give you a quick introduction to what we do. So Blueprint is a data intelligence company, and we are based out of the Seattle area, but we have people all across the world, which is very exciting as well. We focus on customer experience, intelligent supply chain and retail, manufacturing, technology, and the federal government as well. And we work a lot with digital transformation, offering technology solutions that really build digital culture, make employees more productive, and improve satisfaction, as well as the most important thing probably, increasing revenue. So I'm excited to have Alex and Wes to go over this webinar with us. I do want to let you know that if you have any questions at all, feel free to add them to the Q&A. If you are very shy and don't want your name on there, that's totally fine too. You can submit it as an anonymous submission. So any questions that you have throughout, feel free to add them in there, and I will be sure to answer those questions toward the end of the webinar. So just let me know if you have any issues with the audio or anything in the chat, but any questions will go directly in the Q&A. But first of all, I will have Wes give us a quick introduction of what he does at Blueprint, and then Alex can follow right after that.
So hi, hello everyone, welcome today. My name is Wesley Cobb. I'm a principal data scientist with Blueprint, and I work on a variety of projects. The way, as Ruthie was describing, our company is all about data and data information. And I work on a lot of projects that have to do with things like time series analyses and basically helping people model the way they work with their data in a lot of different environments. My background was actually in academia, and I came over and started working on data science about 15 years ago, before it was called data science. But anyway, I've done a lot of work with machine learning and artificial intelligence and computer vision, and I joined Blueprint a couple of years ago and have been having a great time working here since. And I work with Alex, so Alex.
So hi, I'm Alex. I've been working at Blueprint for around 3 years now. I'm a data scientist, and I'm mainly focused on computer vision, but occasionally do other stuff that requires either AI or, Python data science stuff.
Awesome. Thanks so much, guys. Feel free to hop right in, Alex, and get going.
All right. So can you guys see my screen?
Yes, we can.
Okay. So this is the third part of our webinar, as Ruthie said. This is called Deep Dive Inside Collaborative Filtering, because we're going to take a closer look at how recommender systems work. A short outline of our webinar, we'll take a more in-depth view of recommender mechanisms. In particular, we'll look at collaborative filtering, how many types there are, how this works, and what results you can expect from when implementing this in your platform. As Ruthie said, again, we'll do a short recap to refresh stuff that might be relevant for this webinar. And in the first part, Wes gave an overview and talked about attribute similarities. And an important thing he said is that recommendations are used when we want to help the customer choose one or a few out of many, many options. So we do this using data, and the way we use our data depends on the type of data we have. There are mainly 2 types: structural data, which is the foundation of the recommender systems, and targeting data, which helps us actively focus the recommender system. This is an overview, a more visual overview of how the recommender systems work. You can see we have 3 main elements. We have databases, the blue parts. Then we have the user interface and the recommender engine. What mainly happens is that we use the user interface and feed data into the the databases. The recommender engine takes the data from here, uses it to train itself, and then gives us back feedback in form of recommendations. There are basically three types of recommender systems. There are attribute similarity systems, which use content metadata and user information to give us recommendations. We have collaborative filtering systems, which use historical usage, customer historical usage to give us recommendations. And a slightly different one, it's clustering-based systems. Those use product and customer metadata to cluster items or customers. And combining each of those would result in a hybrid system. And sometimes want to combine any of these in order to get better results. In the second part, Ariane talked about keeping existing users loyal, and we do this with quality item recommendations. And also we want to identify new users by understanding purchasing trends in different demographic segments. The key here is understanding user item interactions. Another thing to note is the cold starting problem, which is one of the more difficult problems for the recommender systems. Mainly, the problem here is that sometimes we don't have enough information to go off of, and no information means bad recommendations. So we solve this by gathering information either from the user at sign up or from tertiary sources like cookies or data suppliers. After passing the cold start problem, assuming we have enough information, this allows us to group the users together. So grouping, or clustering as we call it, allows us to recommend items better based on how similar the users are. Similarity can be calculated from interaction, item ratings, geographical data, and more stuff like that. And clustering helps us place new users in a group, even though information about the new users might be minimal. So this is sort of a way we can combat the cold starting problem. After understanding how users cluster together, we can start building archetypes. And an archetype basically represents a generalization or an average of a cluster of users. You can see here, we have a user that has its own features. We estimate the archetype and then we place it in a group, and each group has its own archetype. And after determining our archetypes, we can, by selecting the most important features, we use decision trees to better understand each archetype and tailor recommendations to each users. And here you can see how the decision tree process works. Assuming we have a new user that has signed up on our website and we have some minimal information about them, we can ask ourselves, are their age over 30? So if the age is over 30, we can ask ourselves, have they bought hiking boots? And if they have, are they from the West Coast? If they're not, we will put them in group 2. If they are, we'll put them in group 1 here. And if they are below age 30 and they have brought pre-workout, we will put them in group 3. And you can see each group has its own archetype here. Group 3 is bodybuilder, group 2 is old school hiker, and group 1 is tech-friendly outdoor and sports enthusiast. Okay, so moving forward, what is collaborative filtering, right? A more formal definition is collaborative filtering is the process of filtering or evaluating items through the opinions of other people. And we can identify 2 types of collaborative filtering. We have user-based and item-based. And choosing which one to use out of them is based on the size of user and item database, the available data we have. To have a more informal example, collaborative filtering is something we naturally do as humans. So we can take a example out of 3 people's lives. So we have Julie, Sal, and Matthew, and Julie wants to see a movie, but she can't decide which. So she asks both Sal and Matthew for recommendation. This is user-based filtering because her options are filtered through the views of her friends or her peers. An item-based recommendation example would be Julie trying to decide what movie to watch based on the other movies she previously watched and what she liked about them. So her options are filtered based on the items she previously consumed. So a few takeaways from this: user-based filtering compares users between themselves based on how they rate the same items, and item-based filtering compares items based on how different users rated them. So now it's a good point to talk about the data that we'll be using in our demo, because it's easier to understand the demo and what happens there if we understand the data better. We'll be using data that comes from an online reseller from Brazil. This is separated into multiple CSVs that emulate what their database looked like at the, at the time of exporting. We have over 98,000 orders, over 32,000 unique products. And the good part about this data is that there's no sensitive information. So everything that could be, thought as sensitive or exposing information that shouldn't be exposed has been anonymized. So there's no issues with using this data here. This is what the database looked like. So you can see there's multiple databases and they're tied together by unique IDs. So for example, accessing or tying together data from the orders database and the payments database would be done through the order ID. This would be a unique ID with which you can correlate orders and payments, for example, or orders and order customers through customer ID. For speed purposes, we filtered our data to the top 500 most bought products and top 1,000 most active users. And here on the bottom, you can see sort of an example of one of the databases, what it looks like. You can see the customer IDs are anonymized, so you can't really extract any information from there you're not supposed to extract. And there's a lot of other information here. In order to use our collaborative method, we need a user item matrix. So we will transform the data that we collected through, combining and pivoting data tables. We'll transform it into a matrix. And this matrix will be indexed, the rows will be indexed by product ID, the columns by user ID, and the values inside, or the values themselves, will be the review scores. So this is what the final table looks like, or the matrix. You can see you have product ID on top, customer ID on bottom, and you can see here the ratings this customer has given to this item, for example. So this guy rated this item with a score of 3. So an important question here is, how do we define similarity? There are many measures of similarity we can use, but the most popular one is cosine similarity. And cosine similarity works by measuring the cosine of the angle between two vectors. The smaller the angle between these vectors, the more similar they are. In order to better understand this, we'll use a mock data set, and it's easier to see how this algorithm works on a smaller data set. You can see here we have the 3 people from before, Julie, Sal, and Matthew, and we have 3 movies, very popular ones, and you'll see how each user has rated each movie here. So Julie has rated Fargo with a score of 5, Sense and Sensibility with a score of 2. So from looking at this data set, we can easily infer that Julie and Matthew have similar tastes. If you look back here, you can see Julie and Matthew, they both rated Space Odyssey with 4, Fargo with 4, 5, and 4, and Sense and Sensibility with 2 and 5. But if you look at Sal, we can see that Sal prefers different movies. And it's easy to infer data from a small data set, but the question here is what happens when you have more data? So you have 1,000 movies and 2,000 people. Making observations manually becomes much more difficult. So this is where our algorithm comes in, and we'll use the mock data set to sort of visually represent how the algorithm works. You can see we have Fargo here, one of the movies, Space Odyssey here, the other movie, and we only use, in this example, we only use 2 movies because we want a 2D vector representation. And you can see Julie is represented by the red vector, and she has rated Space Odyssey with a 4 and Fargo with a 5. So the vector goes basically at these coordinates. The same goes for Matthew and Sal. And you can see if we calculate the angle between them, the angle between Julie and Matthew is much smaller than between Sal and Julie. So this is sort of how cosine similarity works. It looks at this angle and says, it's a small angle. These vectors probably point in roughly the same direction, so they must be much more similar than the green and red vector, which have a higher angle. If we use all the 3 movies, we have a 3-dimensional representation. And you can see here the difference is much more accentuated because we also include Sense and Sensibility, which is a movie that Sal has liked a lot, but Julie and Matthew not so much. So you can see the more information we add, the more data we can extract and the more conclusions we can extract from our data. So a side-by-side comparison reveals that the 2D version is easier to follow, but the 3D version retains more information. And this is sort of an insight into how additional information helps our algorithm decide how similar two vectors are. But the more information you have, the better it is. That's the takeaway here. So looking at the mathematical formula of cosine similarity, it might look a bit intimidating, but it's not a very complicated formula. This is just a summation. You basically add these terms together. This is the square root of a number, and this is just the square power of this number. So we'll unfold this a bit later, and we'll see how it works. For now, we need to transform our data into a matrix, as we said before. You can see we have our mock data set here, and you can see the resulting matrix here. It's basically the same numbers, and you can see how the movies are here, right? 4, 5, 2, and the users are here. So Julie has rated each of the movie with a score of 4, 5, and 2, and you can see 4, 5, and 2 here. So it's not a difficult process. It's just we need a more compact representation to optimize our computations. And we can, if we break down the matrix before, you can see this is Julie, Sal, and Matthew. And to give a short example, you can see the similarity calculation between Julie and Sal would work out like this. You can see it's all basic mathematical stuff. It's just the shorthand notation that looks a bit weird. But at the end, it's stuff you can do basically in your head. So you can see the similarity between Julie and Sal is 0.65. This is a similarity score. That's how we call it. If we go through the whole calculations, we will have a similarity matrix. So you can see if you calculate the similarity between Julie and herself, of course, you'll have a 1 because they are identical, right? The similarity between Julie and Sally is 0.65, and the similarity between Julie and Matt is 0.99 because the scores they gave to the movies are, there's not many movies to score, but the scores are very close to each other. So it's almost identical. So 0.65 compared to 0.99 is rather small, right? Meaning that Sal is different from Julie in her movie taste. So now let's put everything together and see how everything ties down. Combining everything together results in the following processing pipeline. First, we pre-process the data, then we calculate the similarities, and the third step is getting a recommendation. So this is a more visual representation of the algorithm. We have the raw data here. After processing the data, we have what we call refined data. And this would be, if you remember when we talked about data a few slides ago, this would be the user item matrix. After similarity calculation, we have the similarity matrix here, and we combine this information here through collaborative filtering in order to have an item recommendation. So you can see collaborative filtering extracts, takes information from the data as well as from the similarity matrix. Okay, so in taking this a step further, we can add another movie to our database, and we'll have it be rated by Sal and Matthew, assuming they saw the movie, but Julie haven't seen the movie. So we have Lord of the Rings here. Julie hasn't rated it, but Sal and Matthew have. And using a collaborative filtering, the computer can approximate Julie's take on Lord of the Rings. After calculating our similarity matrix, we use the similarity scores as weights. The higher our similarity, the heavier the weight is. So the more close two people are in their movie preferences, the more important their take on the movie is, right? A heavier weight means more importance is given to that user's rating. Another thing here, if we want to be more strict in what data we introduce in our rating inference calculation, we can filter users by their similarity. So if a user similarity is below a certain threshold, we can exclude them from our calculation. This gives us a bit more control over how the recommendations and inference work. So you can see here the visual representation of the algorithm. We have the whole data set. We do the similarity calculation between users, and you can see this is the similarity matrix. We've seen this before. We take the similarity of Julie with each of her friends, and Sal and Matthew, we put it here. We take all the ratings from here. So how each of them rated Lord of the Rings, because that's what we want to see how Julie would rate. So you can see Sal gave it the score of 3, Matthew rated it with 5, and Julie hasn't rated it because she hasn't seen it. If we combine these two together, basically we multiply Sal's rating with Sal's similarity to Julie, and Matthew's rating to Matthew's similarity to Julie, we have the weighted score because their movie ratings is weighted by how close they are to Julie when thinking about preferences. So we calculate the mean of these two scores, and we'll have a mean of 3.5, which is, if you only use integers here, we don't want to have any numbers after the dot, we can just round this up to a 4, which you can see is pretty similar to Matthew's score of Lord of the Rings, which is something we would expect. So in the previous slide, we calculated what we call the assumed rating. In essence, we assume that Julie might rate a movie based on how similar she is to the other people we have in our database. If we have more movies in our database, we would use this assumed rating to sort the movies and recommend the ones we think the user will rate the highest. So this is sort of how we create the recommendations. So here we'll have a short demo so you can better understand how the algorithm works. And the demo uses, just a second, uses the data from the Brazilian website you've seen. So here, if you guys still see my screen, you can see we have some users. These are, we use some AI generated faces, so these people don't actually exist. And also the names are random, so they're not actual people, it's just something we did, so the interface looks a bit more friendly. You can see this person has bought, the data is anonymized, so we don't know exactly what the product is, but we know it's a furniture decor category product. The price was 49 Brazilian dollars. And you can see the recommendations based on users that have bought similar items are, she might be interested in health stuff, health and beauty stuff, or a category called cool stuff. We can switch the user here in order to get more, from different people. If we use, we have two ways of recommending items. We can either just simply look at similar people and recommend the items they bought, or we can filter or cluster people, as Irene explained in the previous webinar. And you can see if we use clustering, we'll get a bit more refined recommendations. So you can see this person brought furniture decor, and you can see what's recommended is furniture decor, and something that's a bit more closer to that, it's fashion bags and accessories. So this is more or less how it works. It's not a very complicated process, but the demo helps in running it a bit. So coming back to our presentation here. This is where it's a good point to have a short discussion about profit improvements, or business improvements. The idea is that when recommending items to users visiting your platforms, you want to deliver the best recommendations. So the better the recommendations, the likely it is that a user will either take interest in the item or buy or consume the item. Buying and consuming are basically two different terms for the same thing. If you think about Amazon, you go on Amazon to buy a product. If you go on Netflix, you don't buy anything there per se, but you consume stuff that's there. You consume their items. So in essence, it's the same thing, but it's just called different because of the process. Returning to our e-commerce data set, we can apply our collaborative filtering in order to simulate some profit improvements. So assuming, using our a good system to give recommendations, you assume that people would buy whatever you recommend to them. Of course, not all of them will, but we will assume that 10% of them will buy one recommended item. So you can see here before using these are the initial profits before using the recommender system. We have items here for 2017 and 2018. And after running the simulation, we get the following improvements in profit. So for 2017, you can see November has a huge profit improvement of 16%. December has a 9%. And for 2018, you can see pretty high numbers with using a pretty conservative estimate. So we only use 10% of people, which is a low margin, but we have substantial improvements. So some conclusions from our webinar. We've seen how collaborative filtering works and how it can improve our relationship with the customer. Besides improving profits, good recommendations help business build trust with their customers. So proper recommender systems generate sensible and useful recommendations that are more than just ads. They're a way to engage your customer and know your customer better. If there are any questions, that would be a good time to ask them, and I'd be happy to answer them.
Thanks so much, Alex. That was super, super awesome. We do have a couple questions, so I'm going to read them off to you. The first one is, if there is not enough data on a particular person, how do you decide how much weight their opinion has?
Okay, so this is a good question. This is regarded to the cold start problem. And as I've seen before, I think the best practice here is to, if you don't have enough information, when calculating that person's similarity to some other person's similarity, you will get a low score. So you can filter people that are not as relevant for your customer based on the low similarity score. So you see you don't have enough information, they are not very similar to the person you're currently trying to recommend items to, you just ignore their preferences when you're calculating the recommendations for that person.
Great. The next question is, how realistic is profit improvement calculations, or are the profit improvement?
Okay, so we've used 10% here, which after looking through some data, it's a very conservative estimate. We've seen Amazon report that 35% of their sales is based on recommendations. We've seen studies that show basically 50% of people say that when they're doing their shopping online, they tend to buy items that they didn't plan on buying, but because they were recommended, they ended up buying them because the recommendation was good. So 10% is a low estimate. We could go higher, but even with a conservative estimate, the improvements were pretty substantial.
Excellent.
So I'd say it's pretty realistic, yeah.
And then the last question we have up on here, and if anyone has additional questions, feel free to add them to the Q&A now. But this question says, how large of a population is needed for recommendations to be qualitative or reliable?
Okay, so essentially, collaborative filtering starts from having two people, right? If you have two people that talk to each other, they're already doing collaborative filtering. What you want to do is have enough diversity of opinion when recommending stuff, so you can recommend proper items to different people. This is a sort of a fuzzy question, so my answer is probably going to be equally fuzzy, but you want to have enough people that you don't only focus on a majority of them. You try to diversify the opinions you have when recommending stuff. So it's not a matter of saying a number, so 2,000 people or 100 people or 10 people, but having diverse enough people that your recommendations are just as diverse. Yeah.
Great, thank you. Anything you wanted to add in, Wes?
I was muted, sorry. Yeah, that's a question that people ask a lot of times, the one about how many people is enough people. And the point that Alex was making is the key thing. You have to have enough people that you really do cover the diversity of the target population. In some problems, in some situations, you may only need a few hundred people total in your database. In some other situations, you might need thousands. It just depends on how diverse your expected customer base is going to be, basically. So if you've got a website that specifically attracts a particular type of person with a particular interest pattern, you don't necessarily have to have as many people to actually peg that down as you would if you had something that was more wide open, like, well, an Amazon or a Netflix or something. So it's interesting. Anyway.
Excellent. Well, thank you guys so much. I will be, posting this recording on our social media pages. So if you wanted to catch any more of this awesome topic that Alex went over, feel free to rewatch the webinar. You can share it with anyone as well. I will also, be posting about our upcoming webinar, which is part 4 and the last part of our series. This is going to be an exciting one. We will have Precisely, our partner, on that webinar as well. And that one will be focused a lot on, when you don't have that demand data, what are you going to do? And so some great things to come out of that one as well. So that's something to keep an eye out on. You can follow us on social media. We're on almost every page you can think of. And a quick reminder again that we do have all of the other parts, the part 1 and part 2 of our recommendation systems on our YouTube page. So you can go there and watch it there as well. But wanted to say a quick thank you for everyone who joined. And if you have any questions as a follow-up, you can connect with us on LinkedIn and message us on there. But you can also email us at info@bpcs.com. Thank you, everyone, and have an awesome rest of your day.